So we're in chapter 2 about atoms and elements. And this is a quote from John Dalton. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of sensible magnitude are constituted of a vast number of extremely small particles or atoms of matter. And that was a huge idea at the time. So let's think about that. Graphite, that's the lead in your pencil. Now you push too hard and the tip breaks off. And what if you take that little chunk of graphite and you cut it in half? And you take one of those pieces and you cut it in half. And you keep going. How far can you go? Could you keep cutting infinity, forever? Or is it going to stop at some point? Well, according to John Dalton, we're going to get down to individual atoms, and then we can't cut the atoms in half, right? And the word atom comes from the Greek word atomos, meaning indivisible. So an atom by its nature is indivisible. You can't divide a carbon atom into smaller pieces and have it still be carbon. Now, can you smash an atom into smaller pieces? Yes, you can. That's nuclear chemistry, but what you have left is not carbon anymore. So all ordinary matter is composed of atoms, and if we want to understand how matter works, then we need to understand atoms. In 1827, a guy named Robert Brown was looking through a microscope at some particles that came from pollen grains. And they were suspended in the water, and he observed something that seemed kind of strange. And it wasn't the ads. That was real effective ad. Come on. So there's the pollen grains. And then these are the small particles. And they're wiggling around, right? What's going on? Are they alive? It's like bacteria or something. Yeah, it was good the first time. I don't think we need to look at it again. Okay, so he saw the motion of those little particles, and the question was, what is causing them to move? Well, initially he thought, as it seems reasonable, he thought the particles might be alive. But eventually he concluded that the source of the motion did not come from the particles themselves. It came from the water surrounding them. So in 1905, Albert Einstein developed a theory that explained this observation. It was called Brownian motion because Brown first noticed it. Einstein explained this as it being the result of molecules of water bombarding the particles. We can't see the water molecules because they are much, much smaller than those tiny particles that are visible in the microscope. But the thermal energy of water causes the water molecules to be wiggling around. And they're continuously running into those little pollen dust particles, which causes them to oscillate and to move. And this is a lot like, say, at a graduation ceremony and somebody throws a beach ball out into the crowd, right? So what if you could only see the beach ball and you couldn't see the people? There's people hitting it, right? And the beach ball is just kind of going around randomly as people hit it. So that's kind of the same idea here, that the water molecules are hitting the pollen grains and that's causing them to move. And so this, the existence of atoms was inferred, not proven, but inferred by Brownian motion. And then Jean Perrin later conducted some measurements that confirmed Einstein's theory, and then there was no doubt about the particulate nature of matter. Matter is composed of tiny particles. If you have any questions, feel free to interrupt. So in the 1980s, some scientists at IBM developed or made some discoveries that led to the development of what's called STM, scanning tunneling microscopy. So I'll try to explain it, and then I'll let one of the IBM guys explain it. So we have this probe with a tiny tip at the end, and at the end it gets very pointy, and it really comes down to one atom. And this probe, this tip, is scanned back and forth across the sample being examined. And it's very, very close to the surface, but not touching. And what they're doing is they're running a current that jumps that gap between the atom at the tip and the surface being studied. The current there is extremely sensitive to distance, and so you can get the computer to control the movement of the probe. So it's just gliding along and not quite bumping into the surface. If there's a bump on the surface, then the tip will come up and go around it. And so you can measure these signals from the computer controlling the tip and generate a picture. Okay. So this is a technique that can be used to image atoms and even to move individual atoms and molecules. So this is Japanese kanji characters for atom. And these are written with iron atoms on a copper surface. So these reddish, purpley kind of blobs here, those are individual atoms. Now you see that the resolution on this is not really great. We're not actually seeing what the atom looks like, but we can see, well, there's an atom there, right? Well, how do you move these things around? It's kind of cool. There's a video about that. Hopefully it'll play.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. And that chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Any questions? Let's see if we can. Okay, good. So that's how they made this image, and you can imagine that took a long time, right? Very, very tedious. But they can move a single atom at a time. Of course, you know, that's like sub-microscopic art, right? Nobody's going to appreciate that. But this has a very practical application in that this allows IBM to make very, very small computer chips, because you can make the wires on those chips be 1 atom wide or just a couple of atoms wide, and you can make things very, very small. You can also do things like this and make a very tiny movie. This is just for fun. So, in addition to doing important work, scientists also sometimes spend a significant amount of time on like fun things. So what's the point of all of this? We do have direct evidence that atoms exist. Can we see them? No, they're far too small. But there is good evidence that they exist. Any questions? So now let's try to understand how small they are. So you've probably heard of the Library of Congress. They have 35 million books at the Library of Congress. And if you measure the length of the shelves, 840 miles of books stacked vertically. It's a lot of books, right? So if you took all the words in all of those books and wrote them in letters that were the size of those kanji characters, just a few atoms tall, all those words would fit in an area of 5 square millimeters. That's half a centimeter by half a centimeter. All the words in 35 million books. Atoms are incomprehensibly small. In spite of their small size, they are the key to connecting the macroscopic and the microscopic or submicroscopic worlds. The atom is the smallest identifiable unit of an element. I think of it as like a Lego brick. It's the smallest piece, right? There are about 91 different elements that occur naturally and over 20 that are synthetic, meaning they're not found in nature, but people have managed to make them. They don't hang around very often, though, because they're very unstable, which is why they don't exist in nature. They fall apart.